So what we have here today is a 555 IC, usually used as a timer, commonly used as a timer, but we're going to use it today as a Schmitt trigger. I'm going to show you a quick demo here of it actually in action, and then we're going to go over the circuit itself that we have here, and it's only 4 pieces in the circuit. There's only 4 items in there. Doesn't get much simpler than this. And then we'll go over what the 555, why it's doing what it's doing. So first, let's have a peek at this thing in action. You see over here we have 6 volts. This is the power to it. It's 6 volts on the rails here. This capacitor here is mostly here just so I've got something to clip to. It smooths it out a little bit, but it's not strictly necessary. And this is our input voltage. This is effectively the center tap of this little potentiometer here. And it's hooked from rail to rail, so ground on one side and the 6 volts on the other. So what we're expecting here is it to turn on at about 4 volts. Because of the way the 555 is built, we're going to crank the voltage up here a little bit, and we'll get to getting close to 4 and slow down, and boom, there it is. 4 volts, and I can carry on, of course, up to the rail voltage VCC, which is at 6 volts. And I'll crank this all the way around. Now, you'll notice there's a slight difference here. That's because of the tolerances in the meters themselves. Then we'll go down in voltage. I'll be turning this counterclockwise, and you'll see we'll go past 4. And you might think it should turn off, because it turned on at 4, it might turn off at 4, but it doesn't. It goes down to 1/3 of the rail voltage, and I'll show you why shortly here. And we're getting close to 2. So the reason I put 6 volts in here, because it's nice and easy to divide 1/3, 2/3, and full voltage there. So 2 volts, 4 volts, and 6. So what we have here for the actual circuit itself, it just looks like this. It's awfully simple. We have the 555 itself right here. We have the LED is I wanted some sort of indicator, so that's the green LED here. That's this. This could be a relay, appropriately applied. Throw a right kind of relay in there, and then we got the potentiometer that I was twisting, which is this guy right here at a 10K pot, and we can see here the action of it. When we start out at 0 volts, which is what I did, and it kept going. And we'll notice that the output here is actually at the high. So when this goes low, it's going to go to ground, effectively, and which makes this LED turn on because it's positive on this side. This is the cathode over here when this goes down. So as that voltage that we're applying right here on pins 2 and 6, you'll notice they're shorted together. So as this increases, that's this one here, this is increasing. And then it gets over here to 2/3 of whatever VCC is, in our case 6 volts. And then at 4 volts, this goes to ground. It clamps itself down, and the light comes on. We can carry on going all the way up here to VCC, again 6 volts. Now as we go down, we see the hysteresis in action here. This is a hysteresis curve. And we're going down, there's 2/3. We passed that, which we did. And we got down to roughly 2 volts, which is 1/3 of our applied, or VCC. And suddenly, this went high, and the LED went out. So a quick look here as to why the 555 behaved the way that it did that we saw in that circuit. We can see here a voltage divider based on 3 resistors in a row here from ground to the VCC. And these are equal value, and each one of these is roughly 5K, so 3 5s is a 555. That's where that came from. So as you might imagine, this is at roughly 1/3 of the voltage of VCC, and this spot here would be 2/3 of the voltage of VCC. These aren't exact, they aren't bang on, but you'll see there's a tolerance that's given in the specifications here as to how close these are, and they're close enough for the vast majority of whatever we're going to use. And as a Schmitt trigger, it works quite nicely. Another thing that we can see here, and that you might want to consider a good reason to use the 555, is that it can source and sync up to 200 milliamps. That's enough to run a high resistance coil relay, as an example. But this 200 milliamps, that's at 15 volts. down at the 5-volt level, it's typically 100 milliamps, and that's, again, both source and sink, so that's really nice to see. So if it's down at the 5-volt level, you can use this on many of the single board computers that run at 5-volt levels. There's also a CMOS version of the 555, so if you wanted to run at a much lower voltage, you can see here that this will actually run all the way down to 1.5 volts. I don't know, it's pretty low, but if you've got a single board computer, some of those little guys that run at 3.3 volts, this might be a way to go for a 555 if you need that function of a Schmitt trigger, or you need it as a timer so that your circuit can be doing something busy off on its own while this guy is taking care of some timing, so you don't have to write it in software. Another nice thing about the CMOS version, it runs to roughly it was rated for 3 megahertz. The normal 555 is 100 kilohertz, so kind of a little on the slow side compared to this, but this also does not sink as much current, sink and source. So it's considerably lower, but more than enough for some switching needs. And again, if you want to offload some timing, get it off your microprocessor and just send a timing pulse to this, and it'll do the timing for you while your processor can get on to something else.